can also put arbitrary weights or gains on each of the delayed samples, as this equation shows. The equation states that the output is the sum of past delayed samples, all weighted by different coefficients, which are the a sub i's. Let's look at a bigger moving average filter with some more interesting coefficients. We'll now quit doing this by hand and use Chuck's built-in FIR filter class. We're going to learn what FIR means in just a minute. First, let's look at this code. Here we make a noise object and put it through an FIR filter and set all of the coefficients, 1 through 10, to different values. Let's run that and see what it sounds like. So as we look at this spectrum, we notice some interesting structure. There's a zero-like object here, a dip here and here, some peaks. This is getting more and more interesting, and you might be getting the sense that we could design a filter of this type to do pretty much what we like, and that's true. One way to characterize filters is to put a single impulse equal to 1.0 into it and see what comes out. For filters like the ones we've been looking at, which only use a finite number of previous input samples, then the impulse response only outputs something non-zero for a fixed number of samples. So one more name for this type of filter we've been looking at, aside from moving average, N0, is a finite impulse response filter, or FIR. Let's look at the impulse response of our arbitrary FIR filter that we used before. So instead of running noise through it, we run an impulse through. Here's the code. We've just replaced noise with impulse. Let's listen to that. It's not going to be very interesting. It sounds like a click. But if we look at the spectrum, we see that it's actually a smoothed version of what it did to our noise earlier. But it doesn't have any of the randomness of the noise spectrum. It's just the smooth response of the filter. If we zoom in on the filter itself, the response, we'll see the actual output of the filter is equal to those coefficients that we coded in, and it has a finite length. We put the impulse in, and it only puts out non-zero samples for 10 samples after that. This is all pretty cool, but we need to know a touch more about filters before we can assume that we've got a useful tool or technique that we can generalize from. It turns out that in order to use the impulse response to characterize filters and systems in general, like room reflections and reverb, etc., those systems have to have two properties. The first is time invariance, and the second is linearity. Time invariance just means that the filter or system doesn't itself change over some time period of interest. Our FIR filters from above had constant coefficients once we set them, so they didn't change while we were measuring the impulse response or running noise or any other signal through them. Similarly, the walls of a room don't move around rapidly, and if we assume the source of a sound in a room isn't moving rapidly, and we're not running around too fast, then there is a fixed system of reflections from the source to our ear that isn't changing. So a room is time invariant as well. Linearity for a filter means that only constant gains are applied to delayed versions of the signal. There's no monkey business inside that changes based on what kind of signal we're feeding through it. Strictly speaking, a linear system must obey two properties. The first is called homogeneity or scale invariance. Stated in math, if x yields y, then some constant times x will yield that same constant times y, which just means that if we multiply the input by a gain, we'll see the output go up by the same gain. The other property is called superposition, which means that signals add together linearly. In math, that means that if x1 yields y1 through a filter, and x2 yields y2, then the sum of x1 plus x2 will yield the sum of y1 plus y2. This just means that if we mix two input signals together, the output of our filter is equal to the mixture of what the outputs would have been mixed together if we put each of the individual signals through one at a time. Linearity, both homogeneity and superposition, is what allows multitrack studio recorders and mixers to work. In modern recording studio practice, we can record each singer individually, then mix the recordings together, and it would sound just fine. So what's not a linear system then, you might ask? An example of a nonlinear system might be a simple squarer, or y of n equals x of n squared, which doesn't obey either property of scale invariance or homogeneity. If we double x of n, y of n goes up by 4 because of the squaring. Superposition doesn't work either because if we run two signals together, we get cross products of those two signals. If we can determine and or prove that any digital filter or acoustical system is linear and time invariant, which we abbreviate as LTI, then we can put an impulse into it and completely characterize what it will do to any signal at all. Another name for applying an LTI digital filter to a signal is convolution. We say that we convolve the input signal with the impulse response of the filter to yield the output. Let's look at a different type of LTI digital filter, one that operates on past values of its output. This equation says that y of n equals x of n plus y of n minus 1. So we're operating on the past output value rather than past input values. This particular filter is called the digital integrator and has an impulse response of a constant 1. If you work through this, you can see that initially the response at time 0 is just the input, 1.0. At time n equals 1, then it outputs the now 0 input plus the last output of 1 and keeps doing that forever. Thus, the filter is called an infinite impulse response, or IIR filter, because once it's excited, it puts out a non-zero signal forever. Note that the output will keep adding all the input samples, sometimes called integrating, and may quickly blow up from many signals we could put in. Try it in your own mind or on paper for a constant input, and you'll see that the output grows without bound. Let's back off on the gain of the last output term and form the difference equation y of n equals x of n plus 0.99 y of n minus 1. Now the impulse response is very interesting and actually quite physical because it's an exponential decay, just like we saw in our physical systems. The first output of the impulse response is 1.0, and the next is 0.99, the next is 0.99 squared, or 0.9801. The sequence continues as 0.97, 0.96 approximately, etc., technically forever, because it's an infinite impulse response filter. Let's look at the impulse response for the feedback coefficient set to 0.999. Yep, an exponential decay, but it's much slower. 0.9999 yields even longer decay, 0.9 a very short one, and so on. Let's look at what happens to noise when we run it through this leaky integrator, as it's called. We'll set the feedback coefficient to 0.99. Let's hear what it sounds like and look at the spectrum. Check it out. It's a low-pass filter that has a peak amplitude at 0 frequency and smoothly goes down in gain for increasing frequency. That peak is also called a pole, like a tent pole, and it's the opposite or inverse of a zero. Just like we could use more delayed samples of our FIR or moving average filters, we can use more delayed samples for our IIR or feedback filters. For fun, let's look at this filter. Y of n equals x of n minus 0.995 times y of n minus 2. Note that this uses the output from 2 samples ago. The impulse response looked like this. Whoa! It's an exponentially decaying oscillation. And the single spike in the spectrum tells us that this is a sine wave. We seem to have stumbled onto something possibly quite physical here. In fact, if we remember back to our mass spring damper system, we simulated that system digitally by using 2 delays to approximate the velocity and the acceleration of the mass. So this filter seems to be doing the same thing. In fact, it does exactly that. We've hit on something that is going to be extremely important and useful for our physical models in the future.